I will repeat that the last thing we started to prove, and as Bruce told me, you haven't proved all the theorem. It was the Mitsur-Levitsky theorem. Which states that the n by n matrices over a field K satisfy the standard identity of degree 2n. It was the first part of the theorem, and there was a little bit addition to this theorem, which was that it satisfies no identities of lower degree. So here I recall you, in order to prove this, the second part of the theorem, that, for example, when we study Lie algebras, we say that they are anti-commutative, and we write this as xx equals 0. So the anti-commutativity is hidden here, because this is the square of each element equals 0. But if you replace x with x plus y, you get x plus y equals 0, because this is 0 for all the elements. And also, since this is linear in each variable, this is simply xx plus yy plus xy plus yx. And here you have that x, the commutator of x and x is 0, the commutator of y and y is also 0, and of course this element is 0. So we have that yx is equal to minus xy, which is exactly the anti-commutative law. So this implies this one. And in the general case you can go back in characteristic different from 2. So here, if you want to go here, you require the characteristic is different from 2. Because in this case you simply put y to be equal to z to x, and you get twice xx equal to 0. And of course xx is equal to 0. Something similar happens in the case of arbitrary polynomial identities. For example, if you have an identity of this form, you have, for example, x squared, I write f xy. This is x squared y plus xyx plus yx, for example. And you can do exactly the same. You can replace x with the sum of two things. You consider the expression f x plus zy minus f of xy minus f of z. Okay, this is an identity. This should be also an identity, because the identity means that it holds for all the elements, especially for this special kind of elements. And if you write down this element, you get something when you have x, you have no x squared y and xyx, but you have simply xzy plus zxy plus xyz plus zyx and nothing more. And you see here in the original identity we had something which was a second degree of x, and here you have nothing of second degree of x, but you have one new variable z. So something similar in the general case. There is a fact which is, okay, this is a lemma which I don't want to prove. The proof is something similar like this, that if R is a PI algebra satisfying a polynomial identity of degree n, then R satisfies a multilinear polynomial identity of degree n, of the same degree n. So what is this multilinear? This is linear in each variable. So you have a some coefficient from the field, where sigma is an element from the symmetric group, and you have here x sigma 1, x sigma n. This is a multilinear polynomial identity, where a sigma is from the field. So, from some point of view, if you know that you have any polynomial identity, you know that you have a polynomial identity of a special kind, of this kind. In characteristic 0, you can even prove in the opposite direction, something similar like here. You have a multilinear polynomial identity, you get the original identity. But in characteristic different from 0, you may have some complications. But for many reasons, and for many theorems, it's important to know that the algebra satisfies a multilinear polynomial identity, so identity of this kind. And now if we want to show the second part of the Amitsur-Levitsky theorem, so assume that the matrix algebra satisfies a polynomial identity of degree less than twice n. Then it satisfies a multilinear polynomial identity of the same degree less than n. So you have that f x1 xp, this is some coefficient where sigma belongs to the symmetric group SP, x sigma 1 x sigma p equals 0 is a polynomial identity. And now we use the so-called staircase arguments. There. Okay, this is the staircase. And here you have, this corresponds to E11 from level 1 to level 1. This corresponds to E12. This corresponds to the matrix unit E22, E23, etc. And if you replace F with these elements, E11, E12, E22, etc., you get only one non-zero product, which is simply you get A corresponding to the identity matrix, and you have E1 S, okay, maybe E1 AR, when R, this is something which is the corresponding number. Because here, the matrix units which you use, they are less than 2n, so you have enough thing to do this. And of course, since this is 0, you get that this coefficient is 0. And similarly, you get all the other elements. You can prove even more, which I didn't state here, the only multilinear polynomial identities of degree twice n for the matrix algebra M, N, K are constant times the standard polynomial S twice n, x1, xn, twice n equals 0. This is also some statement. And the proof is similar to this, but we use, so the proof, we use something similar, but what we do, we start with the following substitution. You have, I'm writing this in a graphical way. You have here, you start with this element. In some place you make two loops, and you continue in this way. So you have exactly, so this is 1, 2, this is n. This means that your replacement, this is E11, E12, you have ek minus 1k, then you have ek k, once again ek plus k plus 1, etc. enn. You have exactly twice n elements. You replace these elements in the identity, and you get that f of this is equal to 0. So you get that two coefficients are equal. You have two possibilities. You have two coefficients a sigma plus a tau equals 0, where you choose here sigma is the identity, and tau, this is some permutation in the I plus 1, something like this, where I is maybe even or odd. You have to choose this here. So this is one of the things which you have. And the other substitution you have to do, this is you do the following. And finally you get this way. So if you make this substitution, again you have, you show that two of the elements, because you have only two possibilities to start from here, from one to this, and you get also that you have two more elements of this kind equal. So this, if you do this in the proper way, you can see that all the coefficients, they should be the same up to a sign, and the sign depends on the parity of the permutation. So this is something which is simply not so important. The important thing is first that we have the standard polynomial of degree twice n, and the second part is that there are no polynomial identities of lower degree. This will be used essentially during this mini course. And here I wrote that the only multilinear polynomial identities, because there are two exceptions. So the exceptions here, there are exceptions. This is M1 of Z2, the field of two elements. These are one by one matrices. So the elements of the field, they satisfy the identity x squared minus x equals 0, because this is the Fermat theorem. And the other, this is M2, the 2 by 2 matrices over Z2. It satisfies a polynomial identity of degree 4 in 3 variables. The reason is similar to the reason here. You have some identities which come from that you work over a small field. So I think now I finish with the Mitzur-Levitsky theorem, and I want to continue with the central polynomial.